Recordings rolling. It's Friday, January 9th. We're going to continue should finish this rotational inertia lab from yesterday. Right, so I'll help you guys with that. Okay. You guys know AP. Guys, what are you guys going to have done by the time you guys come to class on Monday? Yeah, Unit 5 on AP Classroom. I'll go over the answers with you guys. Next week, I did cover a bunch of things related to angular momentum and, well, Unit 6 by AP spoke. So I think I won't be able to get you guys the rotational dynamics quiz until after Martin Luther King Day. I do want to do an in-class version, so I have to design some things over these coming weekends. All right, so look forward to there. All right, so you guys had this set up yesterday. Okay. We're trying to figure out what's the rotational inertia of this pipe system about this vertical central axis. And right at the beginning of class yesterday, we're saying, hey, this does kind of look like this shape right here. So maybe we could get an estimate just by looking at these arms, mass, length, from 1/12 ml squared. We did that, we came up with this number. Right? But then we spent the rest of the class going through the dynamic process of putting this in motion and collecting data. Right? And then the bell rings. So we haven't got the answer yet, but we're about to get it. Right? Here's you guys, period 1. Right? So got all this data. And I think a good way to recap this is to take you guys through the ideal rotational inertial lab write-up. You guys remember on the back, I want you guys to do an AP style write-up. You guys remember that? Okay. So actually in front of you, I did print this out so you can refer to this. Now, really, I do want you guys to do this independently, but you can use this to check your answers or make sure you got everything correct. Great. So here's exactly what we did yesterday. Question, what's the rotational inertia of the pipe system about the central vertical axis? We had definitely a meter stick and a stopwatch. You might also include the scale triple Z balance. Sometimes they be assigned to weight, so they don't always expect that, but we use that too. Okay. Right, so that guiding procedure. So I'm looking for what's the basic setup. Then what variable did you measure? Which tool? What do you treat as an independent variable? Like what were you changing in multiple trials? Okay. So here's what I came up with. A set of pipe systems rotate about its vertical axis. Tape a string to the central vertical axis and wind a string around the axis. Route a string through a pulley so a loud weight can be suspended and fall vertically, causing the pipe system to rotate. Boom. That's it. That's the entire setup. Okay, just something real short. That's all I look for. Okay. Using the scale, measure the mass of each weight in kilograms, or each lab mass. Using the ruler meter stick, measure the radius of this central pipe. Okay, record that radius. Using the meter stick, also measure this height change here. I was trying to get the points out of 12, so good ways to write this. Okay, and using the stopwatch, measure the time that it takes to fall that distance. Okay. Then multiple trials, repeat 3 times per lab weight. Now, of course, yesterday in class we just did 2 times per lab weight because otherwise we only got so much class time. Okay, but you probably want to say like at least 3 trials. Right, and then I identified what's the independent variable. You guys remember we were changing out these lab weights throughout the class yesterday? Okay, so it is for maybe at least 5 different masses, which is exactly what we did. Okay, so we went from 0.15 kilograms, 0.2, 0.3, 0.4, and 0.5 kilograms. Right, so that's the whole procedure, which corresponds to the first 4 columns in the lab table. Right, so just measure, 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 measure. See what it says measure up there? Okay, so that's the procedure. Okay. Then these right 4 columns were some calculations, and AP would probably consider that as part of the analysis, maybe. Okay, so that's how I section this. Okay. So how to analyze the data. Determine the average linear acceleration of this bond weight. Remember, we took that first kinematic formula, h equals 1/2 at squared, and rearrange it and solve for a. Right, so a equals 2 times the ball distance over the ball time squared. Right, so we did that for each trial. Determine the tension in the string, which is approximately the weight, but it's a tiny, tiny bit less because it's sort of like a downward accelerating elevator. Okay, so I went through a little derivation process, which again you should be able to do from scratch, but so much class time, so here it is. Make sure you can do this by the time the AP exam rolls around in a couple months here. Okay, so you get the tension in the string. Okay. Then what's the angular acceleration of this whole pipe system? And because what this is eventually heading towards is this expression right here. Right. So like if I want to know the rotational inertia, we're going to do this from a dynamic point of view. We say, well, there's some torque and there's some angular acceleration. And I'm looking at the angular acceleration right here. That's just linear acceleration divided by radial side, which of course is this connection right here. Right. Here's the cross section of the central vertical pipe. You guys remember that? Okay. Get that alpha A divided by R. So we did that. Okay. Determine the torque which is R cross F. So take this radius crossed with this string tension, right? And then we got all these torques. Okay, so we got all that. Okay. And okay, now we're leading up to this graph. So, right, so the last step of last couple steps of the analysis leads straight to the conclusion. And it has to do with this graph that we're about to put together. Okay, okay. And you guys see the conclusion says capital I for rotational inertia equals so many kilogram meters squared. You guys see that? So many kilogram meters squared. Okay. Again, I suspect the answer is going to be pretty close to this from the beginning of class yesterday, but we're going to find out. Okay. All right, so everybody caught up? You guys know where everybody good? Good. All right, so let's put this together. Right now, here, maybe I'll get these averages real fast. All right, so what's the average angular acceleration? All right, see, I think I can do some of this in my head. Like that. 0.0, 0.02. Okay, so I'm just taking the average alpha and the average tau.
No, I just wrote this.
0.059. Alright, so I have those values. Okay, so alpha and tau values. Okay, that's kind of like the x-axis and the y-axis. So these are each individual coordinates. We have 1, 2, 3, 4, 5 coordinates, right? Is that right? Let's plot it and see what happens. Well, I got to scale these axes. Now, I helped you guys out a lot because I gave you guys the title. The title says tau versus alpha. That's torque versus angular acceleration. Okay. The vertical axis says torque in Newton meters. This, of course, already printed on the page. I'm just writing it bigger for the camera. And the horizontal axis says angular acceleration in radians per second squared. Okay. We're doing this whole lab in base SI units, so all the units are good. Okay. All right, all right, we got to scale these axes. So what's the largest angular acceleration? Well, it'd be the one with the heaviest lab weight, looks like, which is like 0.33 something radians per second squared. Okay, so you got to scale this accordingly. So let's go, how about 0.1, 0.2, 0.3, 0.4. So 0, 0.1, 0.2, 0.3, 0.4. Right. Now that will contain all the angular accelerations in this graph. You guys notice I started at 0 and I scaled this linearly? You guys see that? Okay. You guys are following along? Okay. And then what's the biggest torque? It's also the largest slab weight. It looks like 0.07 something Newton meters. So let's go about 0.2, 0.4, 0.6, 0.8. I think that should cover it. So 0, 0.2, or 0.02. Here's 0.04, 0.06, 0.08. There you go. Okay. That will contain all the torque values. It goes up higher than high torque. Okay. Okay. Any question about anything so far? About where any of these numbers are coming from? Okay. All right, so let's plot these points. Right, so first coordinate. When the angular acceleration was 0.055, or so it's a little more than halfway here. Okay. The torque was 0.022. That's bam, right there. First point on the board. When the angular acceleration was 0.099, so almost 0.1. The corresponding torque to make that happen was 0.029. That's right there. Then 0.176, 0.15, 176 probably right there. 0.044, probably right about there. 0.253, 0.059, and 0.334, 0.074. Okay. Right. You guys got your graph too? Put together? Right. Now, what shape do you guys think fits between those 5 points? Is that linear? How many of you guys think that's linear? Linear? It's linear? Okay. All right. So we do line of best fit. Yeah. Oh, yeah. Actually, all these points slide really nice on a straight line, don't they? Line of best fit right there. Oh, wait a minute. Guys, we have a y-intercept. Is that okay? Well, we definitely have to address that because if I was trying to make this, I mean, this is basically the kind of graph we got, right? This would go through the origin. This graph does not go through the origin. So what does that mean? Guys, this is exactly what I was looking for. But how do you interpret this y-axis here? What does that represent? It represents something. This y-intercept right here. It represents what? Oh, okay, yeah. So like the minimum torque you need to get it to turn, right? Because guys, maybe we should have yesterday. Remember, I was saying let's put on at least 150 grams to get it started, right? If we did anything less than that, it actually wouldn't turn at all. Right? Like if you only put on 100 grams, it wouldn't actually turn. But why wouldn't it? It wouldn't turn because there's what? Starts with an F. Friction. This represents the minimum torque to get it to move to overcome the frictional torque. This actually represents the frictional torque in the system. There was a little bit of friction. I mean, the system was not completely frictionless. Now, if you had this like levitating on magnets in a vacuum chamber, then maybe you could get rid of the friction, but that wasn't the case. Right? There was like some parts rubbing against each other. And that's exactly capturing that data there. Right? So the full model equation isn't just torque equals I times alpha. It's torque equals I times alpha plus frictional torque. Okay. Guys, does this look like y equals mx plus b? Is that exactly what that is? Y equals mx plus b? Okay. And what are we trying to find in this lab again? What's the whole goal of the lab? To find the rotational inertia. Rotational inertia. Okay. Which is what property of this graph? The slope. And it looks like pretty much all 5 points are going through this line. So maybe here, what about this? How about points 2 and 5? I think look really nicely aligned. Okay. Now this is where I've heard AP graders talk about this in the past. If your line of best fit doesn't really go through the points, then pick 2 points on the line, not necessarily the points themselves, but 2 points on the line, right? And then find the slope, like rise over run, okay? Which is what we're about to do here. So I'm going to pick this point, points 2 and 5. I'm going to do rise over run. And that slope represents the rotational inertia. Okay? And we're going to get a numerical value on that. Okay? Actually, here, if you look at the analysis, that's what this mentions too. Okay? Right, so last couple points on the analysis section. Graph the 5 points on torque versus angular acceleration graph. Okay? AP might want you to come up with this completely from scratch. Like they may give you just a blank set of axes and say, what variable are you going to put on which axis? Right? They can give you this exact lab question. Okay? And then you say that rotational inertia is represented by the slope of that graph. Okay? So that graph, that'd be exactly what AP was looking for. Okay? So let's get that. So rise over run. So rotational inertia is equal to, I'll say delta tau over delta alpha. So change y over change in x. Right, so that's going to be, let's see, what was this torque? 0.059 Newton meters minus, or what? No, so that's the wrong one. Sorry, get rid of that. I would do this one here. Okay. 0.074 Newton meters minus, say I did this one, 0.029 Newton meters divided by, right, so I'm looking at points 2 and 5, right? Then the alpha 0.3 0.34 radians per second squared minus 0.099 radians per second squared. Okay, you guys see that? Like rise over run. Okay, you guys see that? All right, and calculator time. So 0.074. See what we get. Hold on. Did I have something ridiculous? Here's a point of chamber. Oops. That's a good base with that person. Alright, hold on. That's stop here. For
It gave me 0.2. How about that?
get something.
Oh, that was
Did I type that right? Okay, what are you guys getting?
0.20.
Wait, you're getting what?
0.20.
Okay. You get like 0.19.
That's what I got.
Yeah. Right. Yeah, I know in the past, every time I do this, I get a number that's fairly close to this that we did with this other method. Right. This is off quite a bit. So I don't know why they did. Although I did slap a few times yesterday and numbers don't look radically different. But I know in the past that this answer always comes out fairly close to this, so I don't know why it's off quite a bit here. It's off by a factor of 5, isn't it? Yeah, I don't know, but the process is right there. Okay. All right, so you guys get there? Good? All right, so then for the answer, here it's got 0.191 and then kilogram meter squared. All right. So, guys, if you have all your data gathered and the graph drawn and your math shown, and you also have the write up on the back completed, then you can turn that into grade tray. If you're missing something and you're going to need more time than we have in class today, then it's okay to turn this in Monday. Okay. Okay, so can you turn this in either today or on Monday? Today or Monday.
We calculated.
All right. All right, so you can turn your lab either today or Monday.
Yeah. Is there only 2 steps?
Yeah. That's probably exactly what it is.